Today, we are going to talk about how our assumptions about certain things challenge our understandings and maybe they can be a weakness. So, for example, we know that acids, when they're dissolved in water, their concentrations will contribute to the H positive ions that are there. And in the case of HCl or strong alkalis like NaOH, we've just assumed okay, all we have to do is take the concentration, multiply it by however many H positive and OH negative ions it's going to give, and that's how it's going to be. But that's not the case for many acids and bases. We call them weak acids. If you try to do the same thing, that okay, ethanoic acid gives you one H positive per molecule, and HCl also gives you one H positive per molecule. So you take the same concentration of those, you dissolve them in water, you do everything same, and yet you will not come up with the same pH. And that is weird because theoretically we should be getting the same pH. They both are giving one H positive per molecule, and they're both the same concentration dissolved in the same amount of water. Why is it that pH paper, if you dip it in, it will have different colors? The reason is that our assumption of H positive ion coming from all the molecules that we have added is being challenged here. The assumption is true in the case of HCl. It's a strong acid. It ionizes fully, which means all the molecules that are in there, they take part in this process. But for a weak acid like ethanoic acid, they are not interested in providing any H positive or forming the hydronium ion in water. तो उससे क्या होता है कि if I have H positive, so theoretically HCl and H2O react in similar fashion as H. So they both form H3O positive and Cl minus the anion, and CH3COOH also does the same. But even though this should work, we represent कि इसमें equilibrium is so far to the right and this में equilibrium is so far to the left. It has to do with the bonding, the structure of these things. The dissociation isn't complete in this case. It is very prevalent in this case. So इतना ज़्यादा कि हम इसको reversible की बजाय ऐसे ही लिख देते हैं. Just to show कि जी 100% ionization हो रही है almost. But in this case, the ionization might just be what, 1%, 2%. So clearly that is not happening. So हम यहाँ पर KW नहीं बना पाएंगे because the concentration of acid and the concentration of ions that I get is not the same. It's not correct. So now I will come up with a new equilibrium constant जो हम usually use करते हैं. In fact, I will simplify this to just CH3COOH aqueous ionizing, forming H positive in the ethanoate ion. But because not all of them are taking part in this, मुझे इसकी concentration को देखना पड़ेगा. That this one is going to be H positive concentration times CH3COO minus concentration divided by CH3COOH. The difference is this is coming from the ions that actually took part, and this is coming from the ions that did not. These molecules are still there. They just didn't take part in the ionization process. So for this one, what I will use is what I call ICE method. The ICE method basically tells me what is initial, what is consumed or reacted, and what is at the end or equilibrium. So I'm going to copy this equation here. And I'm going to be like, okay, let's say I have 1% ionization. So let's say I start with 0.20 moles per dm cube ethanoic acid. And there is 1%, 2% ionization. 1% कर लेते हैं. So now the concentration of this thing initially, so ice में हमारे पास तीन rows हैं. Initial, consumed or reacted, and at the end or equilibrium. So this is initially 0.2. This H positive is 1% of that. So initially तो ये 0 है. But जब वो reaction होगा, so this will be 1% of 0.2. So 0.2 times 0.01, यानी कि 1%. That is 0.002 of this. So that is also mole ratio use करेंगे जितना ही है उतना ही है. So this is also the concentration 0.002. I'm assuming that the concentration, because this is 1 dm cube, so concentration or moles वगैरह एक जैसे ही समझ सकते हैं. And this one is going to be the same amount used up. 2% of this is going to be used up. So 0.002 is, sorry, 1% of this is used up. So this is the case. So what am I left with? In this case, it is 0.198. In this case, it is 0.002 because that's how much I have at the end. In this case, 0.002 that I have at the end. So now if I do the Ka or K equilibrium constant for this thing, then here's what I get. 0.002 times 0.002 divided by 0.198. Now, if you think about it, 0.198 compared to Upar wala 0.002, it's a really, really large value. And the 0.002 times 0.002 will give you a value that is ridiculously small compared to the 0.198 here. So we simply say कि देखें equilibrium पे the concentration has roughly stayed the same. So if I actually solve this, I can simply assume this to be equal to 0.2 again. The concentration of initial value is roughly the same as the lower value. And this is extent of ionization of just 1 or 2%. And that is what weak acids do. So it doesn't change much. मतलब अगर मैं इसको actual value करूं तो 0.002 squared divided by 0.198, that is 0.40, then 2, then 0.202 and all that. So this is 0.000202. और अगर मैं यहां पर 0.2 लिख दूं जो ओरिजिनल वैल्यू थी तो इट विल सिंपली गिव मी 0.00002. तो देखें ना, what is difference coming out of this place? Not much. So we assume that since the extent of ionization is low, concentration of acid at equilibrium is roughly the same as concentration of acid initially. And this is going to be the defining factor of weak acids or the solutions of weak acids. Because these values are ridiculously low and they are 2 into 10 power minus 5 yahan pe, we try to use and we prefer to use the idea of pKa here. हम Ka की बजाय जो कि इतनी weird numbers में छोटे-छोटे numbers में होगा, हम pKa का concept use करते हैं. Another important thing that will help us out in this case is that this acid is again coming from a position of very low ionization. So the ions that it produces that are also really, really low in the concentration. If I mix this acid with something else that provides H positive, मतलब इसको मैं एक strong acid में डाल दूं, so जो strong acid के H positive होंगे और जो इस acid की contribution to H positive होगी, उसमें दोनों को ऐड करना पड़ेगा H positive के लिए, but इसके H positive और वो strong acid के H positive won't even compare. इसके 5th decimal place में आ रहे हैं, वो आपको दूसरे तीसरे decimal place में दे देगा. That will be almost 1,000 times more H positive than of this one. मतलब same amounts of HCl and CH3COOH, the H positive that they provide, they differ by factors of 10 or 100 or 1,000. So इसके H positive और HCl के H positive में अगर मैं उनको add कर भी लूं, तो I can simply ignore the contribution of this acid. So उसकी वजह से H positive मेरे पास अगर let's suppose there is a mixture of weak acid and a strong acid, तो मुझे सिर्फ strong acid के H positive को देखना होगा, क्योंकि weak acid वाले की तो value कोई नहीं है. Similarly, if I mix this to any salt which is much more soluble, which ionizes more, and it provides the same anion, then the concentration of this anion, I will also consider this from the salt, the more soluble thing. So it's kind of like saying that a more soluble, a more ionizing thing will overshadow the contribution of this acid. And that is something that we use whenever we have buffer solutions. That is something we use whenever we have calculations of mixtures of weak acids, strong acids, or weak acids and their salts, or weak bases and their salts, or weak bases and strong acids. मतलब सारी जब भी हम मिक्सचर्स में बात करते हैं जहां पे H पॉजिटिव के दो सोर्स हो गए हैं या एनाइन के दो सोर्स हो गए हैं, we only consider the source that is much more stronger, but provided that they differ by a lot. अगर मैं इस वीक एसिड में इसकी कॉन्सेंट्रेशन बहुत ही कम ले लूं और साथ में वाटर भी मैं उसको मिक्स कर दूं, वाटर प्रोवाइड कर रहा है आपको क्लोज टू 7, और ये वीक एसिड भी अगर क्लोज टू इसका pKa भी हमें मतलब क्लोज टू 7 नहीं मिल जाता, 6.9 मिल जाए, तो फिर हम H पॉजिटिव वाटर का और इसका दोनों को इंक्लूड करके देखेंगे, क्योंकि उनकी एक्सटेंट ऑफ आयनाइजेशन इज रफली द सेम. So the Ka depends a lot on the extent of ionization. In strong acids, we assume that it was the same as the concentration of acid. So उसमें हमें ये concept देखना नहीं पड़ा. But now we will consider this, especially if we mix this salt, this weak acid with something else. We will always assume the dominant source is the one that is giving us this value or this value, as long as it is dominant. If they're comparable, then we use both of them. In AS or in A2, they usually don't involve two mixtures जिनमें आपस में comparable value. क्यों? When you add them, you might end up with a quadratic equation. We don't do that in A levels. What we do is we always have mixtures of two things, one of them dominant and one of them not so dominant. So you can easily ignore the contribution of one of those solutions. I'll give you an example and hopefully you will understand this whole idea of comparability and dominance better. Okay, so here's a couple of questions. Let's try them out. So I have methanoic acid, HCOOH. Its pH is 2.4 at room temperature and pressure. And I have 0.1 moles per dm cube of this thing. Let's say I want to figure out the Ka for this. Okay. Now the pH is telling me how the H positive is going on, the concentration of H positive. So pH is 2.4. I mean, I could say that H positive concentration is minus log of 2.4, right? I could say that. Using the calculator, I'll get a value of 0.38. Oh, wait a minute, sorry. This is not H positive, this is pH. So it will be 10 power minus 2.4. pH is minus log, so iska opposite hoga positive 10 की power. So 10 की negative power. Minus log है तो 10 की negative power है. उससे हम reverse करते हैं उनको. So it will be minus 2.4. That will be 0.003981. Okay. Now I also know that methanoic acid, when it dissociates, it provides me with H positive and HCOO negative ion. It's important to remember that it is H positive that's coming out, not this H. And we will study ethanoic acid or other acids in detail, carboxylic acid, when we study organic. तो वहां पे हमें समझ आ जाएगा कि ऐसा क्यों होता है. Mole ratio tells me कि ये जितना मर्जी ionize हो, this and this will always be in the same ratio. That means this is also the concentration of HCOO minus ion, the methanoate ion. So my Ka is going to be HA's concentration, HCOO minus concentration divided by HCOOH concentration. H positive concentration I already know is 0.003981, and that is the same as the other one. So I'll take a square of that. And you can clearly see that this is less than 1% of this value. ठीक है? So इस वजह से हम इसको almost the same रखेंगे. करना तो हमें ये चाहिए कि हम इसमें से इसको minus करें. लेकिन minus करके क्या ही फर्क पड़ेगा? So to keep things simple, we'll just take that as the value. So this divides it and it gives me Ka is 1.58 times 10 to the power minus 4 And that's my answer. Okay. And the unit is also important. So the units are mole per dm cube, mole per dm cube, mole per dm cube. These cancel out. So I'm left with just 1 mole dm minus 3. Okay. So that is how I do it. We can also use the idea of pKa vagera, but before that, can you solve a question for me? What if I have C2H5CWH and the constant is 0.234? I'm just making it up. And pH is 2.77 at a particular temperature, let's say RTPM. Can you find the Ka? Oh, I'm so sorry. So I was saying that the concentration of H positive and this ion is roughly the same. And this is basically the same as this. Now, I have two assumptions here. My first assumption is that the value or the concentration of this ion is the same as concentration of this ion. Now, these are my assumptions, and they are theoretically sound because there's no other source of H positive that I can see, no other source of this propanoate ion that I can see. So they will be the same. If there was another source, obviously they will not be the same. Remember this. The second assumption that I have is that the extent of ionization is really, really low, which means this will be the same as this. And now I can simply plug that in. I get 10 power minus 2.77 squared divided by 0.234, feed it into a calculator, and you get your final answer. You don't have to, even in the exam, you don't have to convert this to a decimal value, then use that here. As long as the examiner can see कि अच्छा बच्चे को पता है concept ठीक है, वो आपको direct इसके answer पे marks देगा. I always prefer to do this. I keep the numbers the way they are until I have to give a final answer. This saves me a lot of time going back and forth using the calculator. मतलब इसका answer मुझे calculate करने की जरूरत क्या है? मैं direct इसको यहाँ पे डालूंगा. ना मैं approximate करूंगा, ना मैं कुछ, मेरा answer बहुत accurate आएगा. Okay? So I would suggest कि आप भी ऐसे ही करो. Now let's talk about these assumptions. What if these assumptions were not correct? What if there was a different source of propanoate ion in the mixture? That is called common ion effect. So let's take an example of this. Let's say I had this same thing, और मैं इसका Ka निकाल लेता हूँ. The Ka of this thing will be, simply plug it in the calculator. That is 1 times 10 to the power minus 5. ये इसका Ka है. Now, Ka obviously remains the same for an acid. It just adjusts if you have something else mixed in together. Okay. Now, let's say I add sodium propanoate salt in this. So मैंने इसमें sodium propanoate salt add कर दिया. And that is, let's say, 0.1 moles per dm cube. What that means is that my assumption that the H positive and the propanoate ion are the same, that is going to be challenged now. Because H positive का एक ही source है. दो sources हैं वैसे तो. One is the source of the acid, H positive acid से आ रहा है, and the second source is water itself. But the ionization of water is really, really small, so इस वजह से H positive का मैं सिर्फ acid को use कर रहा हूँ. So मेरे पास जो Ka बनेगा, it will be H positive concentration times the propanoate ion concentration divided by the concentration of the acid. Now here's the thing. What are the sources? Let me write them. H positive के source हैं acid plus water. So the concentration of acid and concentration of water will obviously वो हमें provide करेंगे H positive. Propanoate ion is coming from the acid and salt. And the acid only has one source, acid itself. In fact, this is acid minus the acid that is ionized. Okay, so this is ionized acid, and that is the remaining acid. Now, let me look at my assumptions here. This value is ridiculously small, so I ignore this. This value is really, really small from this, so I ignore this. And this value is really, really small from this, so I ignore this. And now, using these assumptions, you have to be very aware of your assumptions. Remember, मतलब to be a good chemist, आपको ये पता होनी चाहिए. So now my Ka is simply going to be the acid that is ionized times salt's concentration divided by the acid's concentration. The ionized acid is technically just the H positive. And this I have a common ion effect. This is nothing but one source overshadowing the other source. So Ka still remains the same. Obviously, Ka to acid K behavior pe hai na. So the Ka will still be, what was it? 1 into 10 power minus 5. So it will still be 1 into 10 power minus 5. H positive concentration, let's see. H positive concentration, I don't know because it will change now. सीधी सी बात है. I've added another salt, so it will be X. Concentration of salt is 0.1. Concentration of acid was 0.234. And now let's see how much H positive do I have now. So this will be 2.234 divided by 0.1. So X is going to be 2.88 into 10 power minus 5 mole per dm cube. Is this different from the value I had before? Initially, my H positive concentration was this 1.698 into 10 power minus 3. Right now, it's 10 power minus 5. Notice 10 power minus 3, 10 power minus 5, it has gone down by a factor of 100. 100 times less H positive is available. The acid has tried to adjust the equilibrium because salt ने उसको इतना overshadow किया. So the solubility or the ionization ability of the acid has further been curtailed because of this separate source of salt. And this allows us to make buffer solutions. Buffer solutions are where if you take a weak acid, you take a salt that has the same anion, so it overshadows the salt's concentration. If you have a weak base, then you do the same thing. Okay. So buffer solutions are there to overshadow small changes or overcome or reduce the effect of small changes in H positive ion concentration, a small change in OH minus ion concentration, and they resist change in pH to a small extent. वो equilibrium को अगर equilibrium adjust हो भी रहा है तो वो इसकी और इसकी वजह से वो इतने dominant sources of this ion anion होते हैं और इतने dominant source of the original solution होते हैं, whether it's alkali or whether it's acid, कि उसकी वजह से आपका pH remains the same to a small extent. मतलब of course अगर बहुत ज्यादा H positive आप ऐड कर दोगे और कोई ऐसा सोर्स आ जाएगा जो इसी को ओवरशैडो कर जाए तो obviously that will change the whole game. So a small amount of acid or a small amount of alkali added to a buffer solution doesn't damage it because this stays small and these are overshadowing any impact that's coming out of this. And to do that, we will obviously need acid with the same salt anion wala, or a weak base with the you can also have weak base and its conjugate acid, or you can have a weak acid and a weak base even. वो भी हमें buffer solutions provide कर सकते हैं. So this is simply telling me that the extent of ionization of H positive is much, much reduced, and the pKa and all that will obviously be affected by it. pH अगर आप यहाँ पे देखो, टेम्परेचर से pKa चेंज होता है, pH नहीं चेंज होता. Oh sorry, my bad. टेम्परेचर से pKa भी चेंज हो सकता है, बट इस तरह से एक सॉल्ट ऐड करने से pH चेंज नहीं हो रहा है. Okay, so this one's going to be, what was my answer? Okay, 2.88 times 10 power minus 5 and minus log of that tells me 4.54. So you can clearly see कि मेरे पास शुरू में 2.77 pH थी, अब मेरे पास 4.54 pH है. pH is a measure of the extent of ionization. It's a measure of the strength of the acid and alkali or the concentration of H positive, right? It's not the measure of concentration of the acid. Okay. So there you go. That's the idea of common ion. Now, in buffer solutions, what you need to know is कि किसी भी buffer solution में, sure, there's a whole chemistry behind it. लेकिन exam point of view से they will not ask you a lot of questions about how buffer solutions are made या उनके बहुत ज़्यादा डिटेल में वो नहीं जाएगा. The questions are usually about कि अच्छा ये buffer solution है, what happens to it if you add H positive to it, and what happens to it if you add OH minus to it? How does the balance change? So I'm going to take an example of buffer solution. Let's say I have this acid, ethanoic acid, and I add ethanoate ion to that. Now, the salt can be anything, sodium ethanoate ho sakta hai, potassium ethanoate, any salt that is highly soluble and gives me the same thing. So if you look at the equation of this thing, then CH3COOH is going to give me H positive and CH3COO minus. If I use the terms conjugates, then this is my acid and this is my conjugate acid and this is my conjugate base. What's my conjugate? What's my original base? It's water technically, but मैं बस इसको ऐसे रख देता हूँ. So turns out क्या हो रहा है यहाँ पे? मेरे पास एक base है और एक acid है. So when you're doing the questions of this, वो उसमें आपको 2 marks से usually equation लिखने को बोलता है. So first step you need to do is identify कि आपके इस balance में base कौन सी है और acid कौन सा है. Of course, the base is being shared by the salt that you added. So let's say it was sodium ethanoate salt. So the salt is providing this base, which means this one from the acid is going to be overshadowed by the same ion from the salt. So अगर H positive आएगा तो salt वाला उसके साथ react कर जाएगा, pH change नहीं होने देगा. OH minus आएगा तो acid उसके साथ react कर जाएगा, pH change नहीं होने देगा. ठीक है, क्योंकि ये फिर उसको वापस लेके जा सकते हैं ना, अगर कोई एसिड यूज हो रहा है तो वो इसको वापस प्रोवाइड कर देंगे. सो ओवरऑल द pH remains the same. So here's how you can attempt a question. The question might be like, okay, what happens to it when you add H positive to it? So if I add H positive or I add OH negative, let's see. When I add H positive, the alkali or the base in this equilibrium is going to react, which is this one. So it will provide me with CH3COOH. So you might be arguing कि फिर तो ये acid बढ़ जाना चाहिए, ठीक है? But you have to understand that even if a small amount of acid is added by reduction of this, so that is going to be compensated by the, again, addition of this from the salt. तो overall, अगर यहाँ से reduce हो रहा था तो वो undo हो गया और वो वापस ऊपर चले गए, because वो इस source ने provide कर दिया CH3COO minus. Similarly, if I have, yeah.
Sir, if H plus is reacting with a base, CH3COOH my acid.
Yeah, I should have written
Thank you.
CH3COOH. Thank you for pointing it out. Similarly, if OH minus is reacting, so it will react with the acid, and this will provide me with water and this base. Now you might be arguing कि देखें ये बढ़ गया तो automatically pH या सारा कुछ change हो जाना चाहिए. But at the same time, you have to understand that this one that is being made, it can react with this salt, this ion that's already there. So it will be removed out of the picture. So jitna wo increase hua, is ion ne usko utna hi decrease bhi kar diya, because you have plenty of these ions available. So uski wajah se overall change phir bhi nahi hua aapka jo sare ka sara reaction tha. Another way to look at that would be कि अगर ये कम हुआ है, अगर ये बढ़ा है, because this has been used up. So this is a major source of this thing at the same time. So it will ionize again. Whatever amount is increased, it will go back again and it will be making this again. But then you might be like, hey, ये कहाँ से आया? ये तो अभी बना है. So this is another source of this. So अगर जो अभी बना है वो react ना करे, तो जो ऑलरेडी सोडियम एथेनोएट से आए हैं वो रिएक्ट करके वापस हमें एसिड प्रोवाइड कर सकते हैं. सो अगर ये थोड़ा सा कम हो भी गया, ये यूज करके वापस हमें वो एसिड प्रोवाइड कर देगा. योर पीएच विल स्टिल रिमेन द सेम. Another popular combination of buffer solutions that examiner uses is this one, where you have H2PO4 minus and the other one is HPO42 minus. Again, it might be difficult to identify कि मेरे पास कौन से salts हैं, कौन से acids हैं and all that. So just notice the H positive ion and the charges on the things. This has a 2 negative and 1 H. This has 1 negative and 2 H. So clearly this is going to give me H positive to make this thing. So this is my acid and this is my base or conjugate base. Again, how will the examiner test me? They will simply say H positive add karo to kya hota hai, OH minus add karo to kya hota hai. So H positive will react with my conjugate base. It will give me H2PO4 minus. My acid is going to be produced. And if there's any amount of this reduced, my salt will provide me with the compensating factor. So overall pH will remain the same. Similarly, if this is added, my acid will react with this and it will provide H2O plus the base that is required. And if the amount exceeds a certain threshold and the pH is about to change, the salt can come to the rescue and salt can scoop these out or the available acid can be produced again. Okay. Alkaline buffers पे भी question आ सकता है. Alkaline buffers में a very common example is ammonium chloride. So ammonium chloride को अगर आप देखो तो ammonium chloride में आपके पास ammonia is basically added to like ammonia is the one being made technically. So it's NH4 plus uh, okay, here's a better way of looking at the equation. Ammonia added to water gives me ammonium plus OH minus. Again, ammonia is a weak uh, alkali. So the extent of ionization is low. So this is really small amount. This is a really small amount, and this stays high. The equilibrium's extent is mostly towards the left. At the same time, let's say I add ammonium chloride into the solution. This is going to break down, and the extent of ionization is highly towards the right. So much so that I can simply say this and Cl minus. And again, this is going to be a really high case here because ammonium is going to be dissolved a lot. And this one is a strong source of ammonium. So there you go. This is going to overshadow the contribution of ammonia gas. And at the same time, you have plenty of this thing. So if I make the equilibrium, turns out my alkali is this, or my base is that, and my acid is ammonium. Okay. So now if I need to show the buffer equation reactions, OH plus and this. So H plus reacts with my base. The key is to identify कि आपकी base क्या है. वो है ammonia. So it will form ammonium and OH minus को my acid will react with it, forming ammonia and H2O. And clearly buffer solution is maintaining the pH that is going to change in there. All right. So that is buffer solutions, figuring out common ion effect, and identifying our assumptions. Okay. All right. Allah Hafiz.
Allah Hafiz.